11.6, you may be relieved. Watch these words. You may be relieved to know that this is the last section on series convergence and divergence test of the semester. Yay! In it, we study the absolute convergence of a series, and then we hit the most useful test of them all, the ratio test for absolute convergence. It's a favorite, okay? So I'm going to break this section up into two videos again. One is going to talk about absolute convergence and what it means, and two will go over how to run the ratio test. The root test is, it's in the textbook, people cover it, but I tend to kind of, not really pay much attention to it. I think I have an example at the end. Okay, so let's talk about absolute convergence. So absolute convergence is basically, it's when you take a series and you wrap its terms in absolute values and then determine if it converges or not. So as an example, I've got this guy right here. This is the alternating harmonic series, okay? So let's see if the alternating harmonic series converge, as we call it, absolutely. Those of you that are really paying attention can look ahead and go, maybe draw your own conclusion. Well, you take this series, which is series n is equal to 1 to infinity, and you got minus 1 to the n minus 1 over n, and just for fun, I'm going to show you some terms. So you've got like 1 minus a half, remember this guy? Plus a third, minus a fourth, plus, etc. And what they're telling us to do, okay, is take the terms and wrap them in absolute value, okay? So you're going to sum up the terms, but if they're positive and negative, if they're negative, make them positive. If they're positive, leave them alone. So what we're doing is we're going to just absolute value these guys all the way down the line, and we end up with, well, two ways to write it. One thing is to say series n is equal to 1 to infinity. I'll tell you what to write there in a second, but what happens out here is it turns into not 1 minus a half plus a third minus a fourth. It turns out to be 1 plus a half because you absolute valued that, plus a third, plus a fourth because you absolute valued that fourth term, plus, plus, plus all the way down. In here, that's the same as simply writing 1 over n. So what happens to the negative 1 to the power? When you absolute value the thing, it disappears, okay? Do you see that? Take a long look at that one, because that's how you determine if it converges absolutely. You just make all the terms positive. Then you stare at this series and ponder, gee, does that guy converge or not? The answer is, from memory, hey man, I wanted green. From memory, this is actually the harmonic series, isn't it? What do we know about that guy? He diverges. So our conclusion here so far is that the alternating harmonic series, right, does not converge. Now wait a minute. It does converge, but it does not converge absolutely. Okay? That's the story for this guy. So it does not converge absolutely. But what do we know about the alternating harmonic series? But we know that the alternating harmonic series, right? What do we know about that? It converges. It was one of our first alternating series that we tested, and I would say by the alternating series test. So we already proved that, but it does not converge absolutely. So not this, but this it does. Okay? So we have a name for series that don't converge absolutely, but they still converge. A series that does not converge, right, absolutely, but it still converges, typically as an alternating series, but it still converges with the signs of the terms intact. We didn't change them, we didn't make them positive, but as a natural series, it still converges. Well, a series that does that is said, this is a new word for us, to converge, right? Not absolutely, but conditionally. Okay, so the alternating series, the alternating harmonic series, is an example of that. So we could say something like, we just found something out new this video. The alternating harmonic series converges conditionally. All right, so that just tells mathematicians, oh, okay, it doesn't converge absolutely, but it still converges. Very good. Very, very good. All right, so cruising up a little. What else do we need to know here? Testing for absolute convergence, conditional convergence, or divergence, okay? Here's a big theorem. It's on page 738, and it says the following. It's heavy duty. If a series is absolutely convergent, then it is convergent naturally, okay? If it converges absolutely, then it converges naturally. I don't prove it. There's a proof, I think, in the text, but what it's saying is, if you took a series that had positive and then negative and then negative and then positive, or maybe it alternates or whatever, and you add those guys together and you wondered if they converge, if you make them all positive, okay, all of them positive, and it still converges, okay, that's a bunch of positive numbers being added together. They're either going to go to infinity or they go to a limit. If they converge to a limit, then if you take those numbers and you make them, what, naturally negative again, negative, negative, or whatever, positive and negative together, if you did that, you're going to have a limit also. It's going to be different from if they're all positive, but how the heck is it supposed to go anywhere else if the terms as positive numbers go to a limit, then the terms as positive and negatives go to a limit as well. So all I'm really doing there is waving a hand at that and saying absolutely convergent implies this is a powerful statement. Okay? So problems in the book will come at you the following way. Determine if the series is absolutely convergent, conditionally convergent, or divergent. Okay, here's how you handle these guys. And I use kind of a flow chart for it. I'll put it to the side somewhere. I'll put it way down low. Decision-making tree, if you will. Okay, those of you know computer science or whatever. So if you're asked to do that, your first choice is, does it converge? Absolutely. Question mark. If the answer is yes, then your answer is, hey, the series A sub n whatever converges absolutely. And we just tested for the alternating harmonic series and found that it actually didn't converge, right? But that's how you test it. You make all the terms positive and check it out. If the answer is no, you're not done. You have another decision. Well, does it converge? I said this word, naturally. Okay? All right? So that means, does it converge as an alternating series? If the answer is yes, then you would answer this thing as, well, then the series A sub n converges conditionally. Okay. If you happen to run into one that says it didn't converge absolutely, it doesn't converge as a series, then finally you just have a conclusion, which I haven't seen in the homework yet, but you'd say the series A sub n diverges. So the way you go about this is you come in here, you first check absolute convergence. If that doesn't work, then you check alternating series convergence, and if that doesn't work, then it's divergent. But typically what you get are yes, it does, or no, it doesn't, then check conditional convergence. Here's a couple of problems to check out. Okay, let's do it. So the first one, determine if it's absolutely convergent. So I tell myself, I just go check absolute convergence. Now, you're not done until you show it either does or doesn't. You're able to prove it. So what I do is I look at the series, and I look at 1 over n squared plus 2n. Okay? That's what I check. That is the series without the plus minus happening. When I look at that, I have to hearken back to other problems that I've done, and I go, you know what, that looks like series 1 over n squared. Okay, so you know what I'm going to do? I'm going to do that limit comparison test. Limit comparison test with series 1 over n squared, which is a convergent p-series. Remember, the p in this case is 2, which is greater than 1, so it converges. Okay, so we run the test. We go lim. As n goes to infinity, we put one on top of the other. So I'll go 1 over n squared plus 2n, and I'll divide it by 1 over n squared, and I just do the work. Lim. N goes to infinity. When we invert and multiply, we get n squared over n squared plus 2n. And what do you think that limit is? Well, you look at the lead terms there, and you realize the limit is 1. So what's the big deal? The big deal is we did not get 0. We did not get infinity. So the two series do the same thing. And since this guy converges, we finally can say the series 1 over n squared plus 2n converges. Now remember what we were doing. Okay, we were doing this. Check absolute convergence, and it worked. So here we get to say finally, what happened is our decision went like this. Does it converge absolutely? The answer is yes. So we say series minus 1 to the n minus 1 over n squared plus 2n converges, guess what? Absolutely. And you're done. Because if it converges absolutely, it would converge as an alternating series as well. By theorem. New world, huh? All right, let's go to the next one. We do the same thing. We check absolute convergence. And so we're going to look at the series, but we're going to look at it without the flickering plus minus going on. And we're looking at 1 over the square root of n plus 1. Okay? Well, that looks like, remember this game again? It looks like series, how about I ignore the 1 and just go 1 over square root of n, which is series 1 over n to the 1/2, which is a divergent p-series. Remember, p is equal to 1/2, which is this time less than 1. So it's divergent. We haven't proven anything. We just have an intuition of what's going to happen. You know what I do here is I'll write small, lim comparison test. So I take the lim with, and I would say this, with a series 1 over square root of n, which is a divergent p-series. So in our minds, what we're going to show is that it's going to diverge instead of converge in this case. So we take the lim, we're going to run the test now, and we take our series maybe, which is 1 over the square root of n plus 1, divide it by 1 over square root of n, which is lim. N goes to infinity. I've got square root of n over the square root of n plus 1. If you want to, you can go lim. N goes to infinity of big ol' square root n over n plus 1. And what we're finding is that this limit is 1. So what? So it's not 0. It's not infinity. The two series do the same thing. Since he diverges, this implies series 1 over square root of n plus 1 diverges. There you go. But remember what we're doing. We're checking if it's absolutely convergent. So what that implies is that the series minus 1 to the n plus 1 over square root of n plus 1 does not converge absolutely. Okay? In that case, in the decision, they went this way. No. Now we got to check conditional convergence. All right, so I'm going to put a little note. That's what we're doing. We're going to check, this is the last one, I think, check conditional convergence. Okay, So that means you take the series at face value this time, which is minus 1 to the n plus 1 over the square root of n plus 1. And the only test that works for us there is the alternating series test. You have to run through it, okay? So what we do is 1, we show lim as n goes to infinity of 1 over square root of n plus 1 is definitely 0. We can see that. The denominator gets bigger and bigger. 2, a sub n is 1 over the square root of n plus 1, but 1 over the square root of n plus 1 is a sub n plus 1. That's the very next term, right? So I'm checking to see if it's decreasing, and since the denominator is bigger in the next term, he is smaller, so he's definitely decreasing, all right? So what's the conclusion here? Well, this implies series minus 1 to the n plus 1 over square root n plus 1 converges. And in the grand scheme of things, finally, that implies this series, well, it didn't converge absolutely, but it still converges by, once again, by the alternating series test, okay? It shows that it converges. It doesn't converge absolutely, so now we can state the series converges what? It converges conditionally. And that's what they want you to explore in the homework in this section. That's the first video. We got one more that's going to take us to my favorite and your favorite test of them all, the ratio test for absolute convergence, coming up next. All right.